Okay, so now what we're doing is we're in a new chapter. Your test that you took yesterday, I have checked the ones that actually turned those in, and I have sent out the answers you have wrong. I will be sending the picture of the answers corrections, and if you'll do corrections when you submit it, I need you to submit the old test and the new test if you don't mind, and I will give you your grade when you get finished with that. So, but let's go ahead and talk about our new lesson today on work energy. So here's my one pager. As you can tell, it's more than one. So we're going to talk about acceleration. Acceleration is A equals F divided by M. And then we have these formulas here on showing you how to take our original one and how we can actually incorporate this into our work energy. A system is an object or an object of interest of an external world is everything else. Force applied through displacement is work. SI unit of work is joules, which is J equals 1 Newton times meter. Work being done by a constant force. W equals FD. If the perpendicular force, 1/2 of the mass velocity force squared minus half the mass velocity initial squared, constant force exerted on an angle. And when you're doing an angle, you have to do your F cosine and then your angle number, which is this formula here. Remember, you have to put your calculator in degrees. So, and then it gave us here showing you X, showing you the change in X, changing you the angle. Work done on or by many forces. Here it's talking about how when you have two people pushing a box, there are multiple forces working with that, with the boy on the box and then his friend. It also talked about finding work done when force changes, and it showed you constant force and changing force, and they did the diagrams here. And then it also told you, and this is called the graphical method. When you're doing that, constant force, you use W equals FD equals 20 times 15, which would equal to 30 joules. Change in force, which is this one here, has to do with the force on a string and how it is linear, and that it has, and how to do the equation for that. Then it gives you problem solving strategies on how to do that. We will get back into force diagrams at the end, like we had done before, talking about a system. So you identify and sketch the system, show any force doing work on the system. You do an establish a coordinate system, draw the displacement vectors of a system and each force vector during the work of the system. Find the angle between each force and displacement. Calculate the work done by each of the force using W equals FD cosine angle, and calculate the net force done. So we have an example problem. Our example problem is on the next page. And so let me get to my textbook and let me read to you what the problem says about that example. So it says here, it says a hockey player uses a stick to exert a constant force 4.5 newtons on a 105 gram puck, sliding over the displacement of 0.15 meters forward. How much work is slid on the puck and assumed friction is negotiable? So here we have our variables, and then what we just do is we just do our our calculator. So, to be able to do a calculator. When you're doing a calculator, what you're going to have to do first of all is you have to turn it on. Duh. And then what you're going to do is, since this is an angle, and you know this one is an angle, and since this is an angle, you would have to put that number in. So let's look and see how this is going to work. So since there is a cosine of an angle, and our angle is 0 over here, we don't have to worry about that. So then we're just going to plug in this number, 4.50, 0.150, 1, enter, and that is 6.75 E1, which is the same as that. So, we're going to go on to our practice problems on the bottom here. The first one says, refer to example 1. If the hockey puck player exerts twice as much force, which is 90 meters, newtons on the puck of the same distance, how would be the amount of work on the stick of the puck? And so for this one, because work equals FD, doubling the force would double the work, which would be 1.35 joules. So we just did that times 2. The next one, if a player has a 90 Newton force, but the puck is a constant puck, only half the distance. And so what you're going to do here, if it's half the distance, well, then you divide that by 2 and get the answer. Number 2 says that together 2 students exert a force of 825 newtons by pushing a car a distance at 35 meters. Okay, so the force and the distance. How much work do the students do on the car? Well, so what we're going to do is we're going to take our 85 times our 35 and we get 2.9. If the force is doubled, how much work? Well, then we're just going to take the original equation and we're going to multiply that by 2 to get the answer. Number 3, a rock climber wears a 7.5 kilogram backpack with scaling a cliff. About 30 minutes. The climber does 8.2 meters at this above the starting point. So, what we're going to do is we're going to take our 75 times 9.8 times our distance to get our answer. B, if the climber weighs 645 pounds, so now I'm going to change his weight from 7.5 to 645. How much work does he have to do to lift the backpack? So you're going to do this times this plus that to get your answer. Okay? So then we have practice problem 2 on page 269. It says, a sailor pulls a boat distance 30 meters along the dock using a rope at 25-degree angle. And it says, what is the horizontal and how much work is done on the boat? So for this, we're going to do, all right, here's my force, here's my distance, here's my angle, and now is when I'm going to change my calculator to degree. So you will go down and you will change it to degree. So then we have, open bracket, 255, close bracket, open bracket, 30, close bracket, and then I'm going to do cosine, and I'm going to do 25, close bracket, enter, and I get 6.9 times 10 to the third joule. Number 5 tells us if a sailor, example problem 2, pulls the same force through the same displacement, but the angle now is going to be changed to 50, how much work? So we're going to do the same thing we did up there, and if you want to, you can go up there and enter it, and you can go back, and you can change this to 50, and hit enter. And I get 4.1 times 10 to the third, but look at here, that is a 7, so I'm going to round it to a 2. Number 6 says, 2 people lift a heavy box at a distance of 15 meters. He uses a rope of each with an angle of 15 degrees, is my angle, of vertical. Each person exerts a 225 Newton. How much is worked on the rope? So, for this one, we're going to do the force times the distance, cosine the angle. So we're going to do 255, 15, cosine 15, close bracket, enter, and that gives me 6.5. Shouldn't have a 2 there. So let's try it again. 255, 15, cosine 15. Answer times 2. So number 6 doesn't seem to be working right. So let me look at my work and see if I did it right. 2 times 255 times 15 cosine 15. And let's try again. So 255 15 cosine 15, close bracket, enter, and I still get 7.38 times 10 to the third. So that is the answer. My answer that I have here is wrong, and it is 7.38 times 10 to the third joule. Let me make sure I've got my mode on there right. I got my mode on there right. We're all good. So then number 7 says an airplane passenger carries a 215 suitcase up a stairs, a displacement of 4.0. How much work does the passenger do on the suitcase? Well, since gravity is acting vertically, only verticals should be considered. So you've taken the 215, which is the mass, times 4.2, and you get 903. The same passenger carries the same suitcase back down the stairs. Well, since he's going in a downward place, but there's a vertical, you're going to do a cosine of 180 because he's going down. So you do your 215 times 4.2 cosine 180. So let me try that. 215, 4.20, cosine 180, close bracket, and I get a negative 9.03 times 10 to the second joule. Or, if I change my mode and make it into normal, that is negative 903. I hope you have a good day, and thank you for doing your work.